The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the Great Lakes Seminar Series, co-hosted by the Cooperative Institute for Great Lakes Research and the NOAA Great Lakes Environmental Research Laboratory. It's my pleasure to introduce today's speaker, Mr. Charles Menza, who is a senior scientist at the NOAA National Centers for Coastal Ocean Science in Silver Spring, Maryland. Mr. Menza is a spatial ecologist focused on habitat mapping and modeling, which supports spatial planning in the ocean and Great Lakes. For the past 7 years, he has worked alongside the Office of National Marine Sanctuaries in the Great Lakes and has led several field missions to map underwater habitats. He'll be talking to us today about his work to characterize Great Lakes benthic habitats using remote sensing. Before I turn it over to our speaker, I would like to remind everyone to please leave their microphones muted for the duration of the webinar. You are welcome to enter any questions you have into the chat box at any time during the presentation, and I will read these for Charles to answer at the end of his presentation. With that, I will turn it over to Mr. Charles Menza. Welcome, Charles.
Hi, thank you very much for the introduction, and welcome to all the virtual viewers. Thank you very much for joining me today. So as Mary mentioned, I'm a spatial ecologist. I work for the National Centers for Coastal Ocean Science. I'm stationed in Silver Spring, Maryland, but I feel like sometimes my heart is up there in the Great Lakes region. I try to go there as often as I can, and really enjoy the community and being out on the water. So in this seminar, I'm going to present on a collaborative effort by the National Centers for Coastal Ocean Science, the Office of National Marine Sanctuaries, and the Great Lakes Environmental Research Laboratory to explore and characterize benthic habitats in Lakes Michigan and Huron. This effort includes the collection and analysis of new multibeam bathymetry surveys, interpretation of existing nearshore LiDAR surveys, and ground truthing from underwater videos. A guiding principle in this work is that high-resolution, remotely sensed bathymetry and reflectance data can effectively characterize benthic habitats and other submerged resources in the Great Lakes. Before I dive in, I want to take a moment to acknowledge the efforts of my colleagues at NCOS Sanctuaries in Gloro, because they've worked very hard on collecting and analyzing the data sets that I'm going to present on. So we have Matt Kendall, Tim Batista, Will Sauter, Ayman Mabrouk, Sarah Heil, Bethany Williams, Brendan Guthrie, and Rachel Husted from NCOS, Russ Green, Stephanie Gandula, Phil Hartmeyer, Wayne Musardi, Ellen Brody from Sanctuaries, and Dennis Donahue, Travis Smith, and Bo Bramer from Gloro. All of these people have been instrumental in getting us to where we are today, helping collect information and interpret it. So probably most of you are familiar with Gloro and Sanctuaries. They've been doing research on benthic habitats in the Great Lakes for a long time. NCOS, and in particular, their work on lakebed mapping is a little bit newer to the scene, but we bring a lot of experience from decades of mapping in other locations. We've worked out in the Pacific Territories, in the Caribbean, along the east and west coasts. And I think this experience is relevant because it brings lessons learned across a range of bottom types, and working with a diverse group of people that may be helpful in the Great Lakes as well. So for instance, the analytical framework we have adopted, and I'll talk about a little bit later in this presentation, was honed mapping coral reefs. So I think there's a lot that NCOS can bring to the table, and I hope that you all will agree. So I'm going to talk a lot about data that we've collected in 5 specific project areas. From 2016 to 2019, our mapping work is focused on these 5 sites. And they all occur within to support the Office of National Marine Sanctuaries. Sites near shore, Wisconsin, off Manitowoc and off of Sheboygan are located within the proposed Wisconsin Shipwreck Coast National Marine Sanctuary. Sites at Micheley Reef and on the Alpena Amberley Ridge were chosen to support Thunder Bay National Marine Sanctuary. More recently, just in the past year, INCOS, GLURL, and Sanctuaries has also started mapping work alongside the Office for Coastal Management at NOAA and the National Park Service in Lake Superior to support the Great Lakes Restoration Initiative. At each site, except for nearshore Wisconsin, remotely sensed lakebed mapping data comprising bathymetry and lakebed reflectance were collected with the objective of characterizing lakebed habitats and identifying submerged resources. And I just realized that I did not click next. You're not seeing my map. There you go. At nearshore Wisconsin, we used an existing remotely sensed bathymetry dataset collected by the Joint Airborne LiDAR Technical Center of Expertise in 2012 with the purpose of extending our survey off of Manitowoc to the shore, and also as a proof of concept to see what existing LiDAR information could tell us about the lakebed. This was one particular area, so just the nearshore Wisconsin site, where we didn't have reflectance data, and our lakebed maps were developed exclusively from bathymetry data. So just talking a little bit about Benthic, we understood these areas had important benthic habitats as well as other submerged resources before the studies began. We understood from folks like John Jansen and Titus Seilheimer from the University of Wisconsin and Sea Grant that there was hard bottom sites off of Wisconsin and that there were historical spawning grounds for lake trout and yellow perch. At Micheley Reef, we knew scientists like Ellen Marsden had studied the reef, and we knew that there were natural spawning populations of lake trout. And we also knew that there had been forays out to the Alpena Amberley Ridge by researchers such as John O'Shea, and had found abundant hard bottom. So our intent was to support and build off of this previous research by collecting high resolution lakebed mapping data where there wasn't any yet. At several of the sites, the lakebed was mapped only by older soundings used for nautical charts. Some of these soundings date back to the 1950s. And they provide a very coarse understanding of the lakebed shape, but are inadequate to define the nature, extent, and condition of many of the habitat characteristics that are of interest to ecologists and managers. So for instance, they can't see cobble fields, mussel beds, or clay outcrops. And the cobbles that are shown in the picture here definitely can't be seen by these older soundings or in nautical charts. And yet we know that the distribution of these sorts of things are really important for making decisions to protect, monitor, restore, and sustainably use the Great Lakes. So the rest of my seminar is going to focus on answering these 4 questions. And I'll start with, how can benthic habitats be efficiently and accurately mapped? And so there are many different technologies one can use to map the shape, texture of the lakebed, as well as distributions of many benthic species. All of the technologies shown on the slide here use lighter sound waves to remotely sense the lakebed. The fact that they are remote allows them to see a larger perspective and therefore gain survey efficiency compared to more in situ observations. We focused on using LiDAR and multibeam echo sounders and side scan sonar systems because of the depths we work in. Both LiDAR and multibeam echo sounders can create very accurate 3D images of the lakebed surface. They do so by precisely measuring the amount of time it takes for light or sound wave to be reflected off of the lakebed and returned to the receiver. And they look like this. So this is a map of Mischli Reef that we collected using a Kongsberg 2040C multi-beam echo sounder. It's an example of what you would expect to see in any bathymetry surface collected with a multi-beam. Each pixel corresponds to a 1 by 1 meter measurement of the lakebed. The purple and darker areas are deeper. The yellow and orange and redder areas are the shallowest. And you can clearly see Mischli Reef emerge from this background of flat, fine sediment. So the area in blue and purple. One of the advantages of creating a continuous bathymetric surface is that the lakebed can be mapped and characterized across a continuum of spatial scales, from the resolution of the pixel to the footprint of the entire survey area. This is useful to get a better understanding of spatial connectivity among habitats and address species and habitat relationships which function across more than one spatial scale. And we've found bathymetry to be ideal at detecting topographically complex structures. So if you can see my cursor here, the dredge deposits over here on the left-hand side of the screen, and the ridges comprised of boulders and cobbles along the edge of Mischli Reef. We've found that it's more, we have a more difficult time accurately distinguishing particle sizes in fine unconsolidated sediments, like out here, where everything is just flat. The bathymetry doesn't vary, and so we can't distinguish those types of things. But it just so happens that LiDAR and multibeam echo sounders can tell us a little bit more about the lakebed if we look at the intensity of the returned sound or light signals, in addition to the time it takes for them to bounce back. And side scan works in a similar way, looking at the intensity of sound returns, but it won't give us depth. This intensity return is commonly referred to as backscatter, and it provides a two-dimensional image of the lakebed surface reflectance. So here you can see in this image for Mischli Reef, the backscatter from the multibeam echo sounder. And I've outlined 4 distinct areas on this map that can be distinguished by backscatter, but can't by bathymetry. If you looked at these areas in just bathymetry, they would be completely flat. You wouldn't be able to tell that they are different. But here you can see the backscatter changes, and areas that are darker have absorbed more of the sound and appear or are silt. Areas that reflect more of the sound are lighter, and so things like bedrock and pebbles really come out because they're more reflective. And those 2 remote sensing layers, bathymetry and reflectance, don't provide the entire picture of the lakebed. Alone, they can tell us that the bottom changes, but they can't label what those differences are. So for instance, the additional information needed to verify the substrates in this particular image required additional data from ground truthing. So ground truthing takes many different shapes. We are trying to get eyes on the bottom to determine what the patterns in remotely sensed data are. And usually this requires a substantial amount of effort. For the projects that we've been working on in those 5 project sites, we've typically used diver transects and drop cameras, but we've also acknowledged that the use of sediment grabs and ROVs would be very beneficial. They'll collect slightly different types of data that you can't with a diver transect or a drop camera. Across all our project areas, we extensively ground truth remote sensing data so that we could label specific topographic patterns and textures. Most ground truth sites were discrete points to verify a feature, but we also made use of transects to more efficiently collect data at clustered sites and also to look at gradients. Spatial positioning has always been a key determinant of the data quality of ground truthing data because sites need to be overlaid very precisely onto the bathymetry and backscatter surfaces. Our approach has been to use a differential geographic positioning system on a boat and measure relative distances between the boats and either divers or cameras. And that's been sufficient for our purposes. We feel like we've been able to get to within 3 meters of a particular point in shallow water and 5 to 10 meters in very deep water. You could get improved spatial accuracy, but you would need to make an additional investment in special equipment like ultra short baseline acoustic positioning system. So this is what ground truthing looks like. This is a map of different lake bed types off of Manitowoc, classified by, and then all of those dark X's, those dark crosses represent where we dropped a camera to collect ground truthing information. And I wanted to show this map because the magnitude of the ground truthing effort is a major factor affecting the level of detail that you can extract from a remotely sensed map. The more habitat characteristics you want to understand, the more ground truthing information you're going to need. To clearly define relationships between ground truthing observations and remotely sensed data, you need to cover all the features and classes of interest. You need to consider replication. You need to assess environmental gradients and also ensure geographic representation. You can't cluster all your ground truthing sites off in one zone of your map. In my experience, the number of bottom types you can classify and the accuracy of your maps is directly related to the amount of effort you put into the ground truthing that you do. So this map shows approximately 54 square kilometers of insonified bottom and about 100 different sites that we used for ground truthing. It took about 3 days to accomplish this, and it's actually only half of the ground truthing field work. There's an additional set, an independent set of ground truthing information that we collect, that we use to assess the accuracy of our maps. We make sure that it's independent from this, this initial ground truthing effort, and basically doubles the time we're in the field collecting in situ observations. So it's a large effort, and that's the point of this particular map. The next slide the next question I wanted to answer is, which habitat characteristics can be mapped by remotely sensed lakebed data? Now I'm going to show a series of maps, also off of Manitowoc, to showcase what those characteristics are and what one could expect using similar mapping efforts. Since different people may describe the same bottom characteristics in different ways, we've adopted the coastal and marine ecological standard for labels and thresholds. So if you're familiar with CMEX, you might see particular keywords that are used extensively to map the geoforms, substrates, and biotic coverages. So this map here shows the geomorphic and structural features off of Manitowoc. We see a large proportion of the bottom covered in moraine. Also some of the area just offshore of Manitowoc Harbor, classified as glacial lacustrine deposits. This was kind of a surprise to us. We weren't expecting so much moraine or glacial lacustrine deposits when we started this. We certainly knew that they existed in the area, but just the extent was quite a surprise to us. I'm showing here a red line because it separates two different project areas for us. On the right-hand side, so towards the east, we collected data with side scan and multibeam. Closer to shore on the west, we collected, or we didn't collect, we used already existing data, LiDAR data, to make interpretations. And I just wanted to showcase that you can create a seamless map of geomorphic and structural features from those pretty different data sets. And that was one of the tests we had when we started the LiDAR interpretation. This particular map shows substrate. So we can see how fine unconsolidated sediments and gravel are dispersed throughout the survey area. And just thinking back a little bit to the preceding map, you can see that gravel mixes and the gravelly habitats are mostly where we have moraine and glacial lacustrine deposits. This map here shows species distributions, or a species distribution for mussels. We were able to accurately map mussel distribution off of Manitowoc where we had reflectance data. So you can see all of the area where only LiDAR data existed, which was very close to shore, and where we didn't have reflectance data, we weren't able to map mussels very well. And so all that's grayed out. We also were able to map biotopes, which, if you're familiar with CMEX, this is a term they use to reference the combination of abiotic habitats and species distributions. What's kind of neat in this image here is you can see three different major biotopes found off the shore of Manitowoc. There's mussels attached to the coarse gravel, represented by the dark reds. There are sparse mussels, which are mostly attached to cobbles intermixed with hard clay. And then there are mussel beds on fine sediments. So those are mussels that aren't attached to any coarse gravel. They're just on top of fine sediments. And a neat thing we saw here was a pretty strong, easily distinguished edge along a very specific isobath. And I've always wondered, does this particular edge continue to the north and south of the survey area, or is it more of a localized correlation? So another aspect of the bottom that we were able to detect in remotely sensed bathymetry and reflectance data were human impacts. We could see here based on the dark black lines that where I guess the city of Manitowoc had placed pipelines underwater, extending from the city. And we could also see a whole bunch of what we believe are dredge deposits, a kilometer or two off of offshore of Manitowoc Harbor. We weren't prepared for the number of dredge deposits that we saw. We probably saw 70 to 100 of these sites, and we didn't even capture all of them. You can imagine how they changed the bottom habitats by greatly increasing the quantity of cobbles and other substrates that mussels and maybe even fish may aggregate to. Some other mapped benthic characteristics, we were able to quantify bedrock and hard clay, boulders, cobbles, all of the variables on this list. We also tried to quantify the amount of macroalgae that's loose and floating along the bottom and fish, but we weren't able to do that accurately. We just didn't get enough information to do that, and I know it's of interest to many people. I wanted to talk a little bit about uncertainty and how it relates to what you can describe on the bottom. It's a key process in map making to assess how accurate or how uncertain you are when you're making maps. We developed these confusion matrices, which show the comparison between lakebed classes that you've observed versus what you've predicted. So everything along the highlighted diagonal identifies where your predictions are the same as what you've observed, and anything off of that diagonal is what you've gotten wrong. And matrices like this are used to help determine what classifications you can use. You might remove a class, or you might combine different classes. And I wanted to include this slide in the presentation because accuracy assessments are occasionally omitted from mapping projects. And I think it's really helpful to make an objective determination of what can and can't be mapped, and also to show managers what sorts of information they can use with and without caveats. So moving on to the next question that I wanted to answer. How can modern analytics support benthic habitat characterizations? And in particular, I'm thinking of artificial intelligence. There's been a lot of buzz about how we can use computers to make more objective decisions, and we tried to apply that in benthic habitat characterizations and lakebed mapping. And I wanted to show you, what that looks like. So our general analytical framework looks like this. We take bathymetry and backscatter reflectance data. We extract features, sometimes referred to as objects. We ground truth them, and then we develop maps for characterization. There's two steps in this process where we think artificial intelligence may play an important role. In 2016, when we made maps for Wisconsin, we manually digitized and classified all lakebed features. So that was me or one of my colleagues with a mouse digitizing on a computer. And so you can see, and we acknowledge this could be pretty subjective, but it's also a very commonly used methodology, and it's well vetted. So in comparison, today, while we create maps of Mischli Reef and along the Alpina Ambuli Ridge, we're applying mathematical models to do the same thing. And by doing so, the steps that used to take us weeks, after some setup, can take minutes, which is just kind of mind-boggling. If you want to add a new data set, if you want to test a new hypothesis, once you invested the time to set things up, you can change things without a substantial effort at all. And just digging in there a little bit, thinking about feature extraction and how artificial intelligence could help there. We use a workflow honed by my colleagues, Brian Costa and Tim Batista, in coral reef environments that uses derivatives of bathymetry like slope and bathymetric position, variance, and rugosity to better describe the bottom shape and texture. They use those derivatives, bathymetry alongside backscatter, and they sometimes look at these things across different spatial neighborhoods to look at different spatial scales. They then combine all of these data sets together, usually using techniques like principal components analysis, and enter them into an agglomerative algorithm software package in Envy, which segments these data into different zones. So the map on the right shows what the final segmented bathymetry, backscatter, and derivative layers look like. Each of those segments represent internally homogeneous zones of the lakebed and a feature that could be labeled. So the other step in the process that one could apply artificial intelligence is with classification. We tested many different methods for classification, some that didn't use things like machine learning, more commonly used things like logistic regression, beta regressions, but also machine learning like gradient boosting for regression and support vector machines. We ultimately landed on neural networks because it consistently provided more accurate models when we compared it against our independent accuracy assessment data sets. This figure here shows the neural network that we use to classify substrate at Michigan Reef. So you can see on the left, metrics defining features from remotely sensed layers enter the network. They are processed at nodes in 3 different hidden layers. And then as outputs, we get feature labels corresponding to the substrate classes. And this is what the output looks like. It's a substrate map of Michigan Reef. We get results. This particular substrate map is 80% accurate. When we look at our confusion matrix, we can see that we do a really poor job of distinguishing between gravel mixes and gravelly substrates. So if we combine those 2 classes, we can boost our accuracy to 90 or 95%, which when you're dealing with lakebed mapping is pretty good. Another output from using neural networks is muscle coverage. We can see that using this modeling technique, we have lots of mussels found on top edge of Michigan Reef, but also in the dredge deposits that were detected in the remotely sensed data off the reef amongst the flatter, fine, unconsolidated sediment habitats. So that brings me to my 4th and final question. How can lakebed mapping and benthic habitat characterizations be scaled up to the rest of the Great Lakes? I presented on an approach that focuses on specific areas, but the Great Lakes is very large, and there's lots of places people want more resolution, more lakebed mapping data. And we can acknowledge that not all the areas are equally important. So how do we map the rest of the Great Lakes? And I think to do that, we need to prioritize our mapping efforts. In the project areas that I've shown today, we had developed a prioritization framework, digital tools, and asked managers and scientists where they wanted additional lakebed mapping information. Since that request was inherently spatial, we used a participatory geographic information system as our framework of inquiry. We asked respondents to place virtual coins on a spatial grid, as well as provide justifications for their coin placements. This effort showed where more mapping data was needed. It gauged the interest levels and importance of those locations, and it identified specifically what sorts of lakebed mapping data were needed. Sometimes people didn't need everything under the sun. Maybe they needed just one particular data set. And so these results were published in 2018 and in 2020 for Wisconsin and off of Thunder Bay and the Thunder Bay National Marine Sanctuary by my colleague Matt Kendall, who is the lead author on those reports. I also want to mention there's ongoing work by other groups that are also doing mapping prioritizations. The Great Lakes Bottom Mapping Work Group, the NOAA Interagency Working Group on Ocean and Coastal Mapping, the Office for Coastal Management. They've all undertaken mapping prioritizations that have either focused on different areas or are performed at broader spatial scales. All of these prioritizations can help support where to go to next. And then in addition, the Marine Technology Society, Great Lakes section and Northwestern Michigan College are working on strategies to facilitate how to do more mapping in the Great Lakes. So I just wanted to mention those other groups that are doing great work. This slide shows an example of what you get from a prioritization. This one here is looking at the results from Thunder Bay National Marine Sanctuary. In the largest map, showing where respondents identified that more habitat mapping data is needed. In the top right, where more archaeological data was needed. And then in the bottom right, shows the number of respondents that showed interest in each particular grid cell. So you can see it in this map where someone may want to go to next, but it's also useful because you can see who else was interested in a particular area, where maybe you could talk to others about enabling a partnership or developing a collaborative proposal. On the other hand, it may show that you're kind of alone in where you might want to map, and so you either should maybe consider focusing on a different area or making sure that you have the resources to go alone. The prioritization in Thunder Bay National Marine Sanctuary included 24 different respondents from many different offices. It included scientists and lake managers, and collaboration was important for the prioritization, but it's also really important for the next phase as people try to get in the water and collect lakebed mapping data. Collaborations help share resources. They teach each other lessons learned, and they can keep the momentum going better than if people are doing this individually. So one other strategy that I think is incredibly valuable to consider as we think about scaling up lakebed mapping to the rest of the Great Lakes is communication. I've described a lot of different data sets, remotely sensed data sets, ground truthing imagery, interpreted products can be very large. And I'm thinking, storage-wise, how many gigabytes of data you need. And they can be pretty complex too. Sometimes when you have that amount of data, it's hard to sift through it and figure out what patterns are important to be considering. And we need to find ways that brings these data sets to decision makers and brings the data in a way that that allows decision makers to effectively make sense of all this data. So this slideshow here shows one online tool that NCOS, Sanctuaries, and Gloral projects have used to present imagery, maps, and videos. It provides all the mapping information in one location. It allows users to navigate across the project area, panning around. You can zoom into specific sites, if different scales of information are important to you. And it overlays all the information so that users can see how multiple layers are associated. You might want to see how imagery is connected to an interpreted, classified lakebed map. And one of the really cool features is that you can click on each of the sites where we collected ground truthing data and see underwater videos and interpretations. So I have up on the screen here kind of the map of spatial data on the left-hand side. I've already clicked on one of our ground truthing sites, and you can see that the video is starting to spin up in this screen capture. I know that there are many other similar communication tools out there. I'm familiar with the Great Lakes Observing System, Digital Coast, the Great Lakes Aquatic Habitat Framework, but I know that there are many others as well. And I think all of these can play a role in promoting lakebed mapping and helping communicate where important data exists in the Great Lakes. So my last slide is just kind of a hodgepodge of scaling up lakebed mapping in the Great Lakes. For one, we reused existing nearshore LiDAR data to map off of Wisconsin. And we proved that there were certain benthic habitat map characteristics that could be accurately mapped. A lot, or maybe all, of the nearshore US coast and the Great Lakes has already been mapped with LiDAR, but it hasn't been interpreted yet for assessing and classifying benthic habitats. So I think that's one cool future direction that someone could take. Another is, I'm not sure if folks are aware, but there's talk now of bringing a NOAA white ship that are typically used to survey the oceans to the Great Lakes. So what a cool thing if we have a white ship up here for a long period of time, banging out a lot of data collection in the Great Lakes and supplying the decision makers with the information that they need. There's a lot of work and talk now also about automated bathymetry processing. I didn't really get into that in this seminar, but a lot of work goes into processing bathymetry and backscatter data. You need to clean it. You need to make sure that it's standardized. But there are people out there trying to use artificial intelligence and mathematical models to automate all of those processes. I also split two of the important processing steps that I talked about, the feature extraction and the classification, into two separate steps. There are also people developing deep learning neural networks to combine both of those things together. So looking at one image, and in one step, you can spit out classified benthic habitat maps. There's going to be a need to map deeper areas, and so I think automated surface and underwater vessels are going to be really important. I've heard of people starting to use those. Peter Esselman at the USGS I think Guy Meadows, they're all thinking about, how do we get additional data in these deeper environments and still get high resolution information. And then as we collect more data, we might start shifting from just collecting baseline information to starting to be able to detect changes, to monitor the lake bed as we collect data over the same spots in more than one instance. So just I wanted to mention all those things because I think they're exciting. I think that there's a lot of momentum with lakebed mapping and trying to use that information for assessing and characterizing benthic habitats in the Great Lakes. And it's just really cool to be working here with all the other people that are thinking about the same sorts of things. So with that, I guess I'll hand it back to Mary and say thank you very much again for listening.
Thanks a lot, Charles. Great talk. Very interesting stuff. We do have several questions that have been entered into the question box. So I'll encourage others that have questions, please type them in the box and I will read them off. So first question from Margaret Lansing at NOAA Gloral. She was referring to a reef that you showed, an image that you showed earlier in your talk, asking how tall it was from, it had purple and red, so from the purple to the red. This was about 10 minutes into your talk. I don't know if you're able to get back to that.
I think it was for Mishley Reef. I don't have the data at my fingertips, but I think it was about 20 to 30 feet off the bottom.
Okay, great. Thank you. Next question from Saeed Mamari from Michigan State University asks, to model or measure mussel distribution and density, what efforts and data should be employed?
I think it depends on what you're trying to get. There are people that have already developed core scale models of mussel distributions. If you want to have higher resolution maps, so maps similar to what we were showing, you need to have the remotely sensed mapping data at the resolutions you're interested in. And you also need to have an effective ground truthing program to measure where mussels are and in what habitats they occur in. I hope that answers your question.
Okay, thank you. Next from Bopi Badanda at Grand Valley State University. He first says, thank you for revealing so many cool lakebed features in the Great Lakes. And then he asks, NASA deployed ICESat-2 for assessing ice in 2018. Users were pleasantly surprised to find it revealed coral reefs in amazing resolution because its green laser can penetrate 40 meters below the surface. Are you aware of ICESat-2 data are available for the Great Lakes region?
I don't. And I would direct you to maybe Brandon Crumweedy at the Office for Coastal Management. I know that he's very familiar with a lot of the data sets that exist in the Great Lakes and may be able to answer your question. But following up on that, the invasive mussel explosion that occurred in the Great Lakes has been disastrous for many reasons. But one thing it's allowed is for water clarity to increase. And so I do know that LiDAR data is able to penetrate deeper and deeper as water clarity increases. And I think the data sets that we used got to about 30 feet. And I think I've heard recently that LiDAR data, using lasers can get down to like 70 feet now, which is crazy, but also very helpful.
Right, thank you. So Steve Ruberg has a couple of questions. First, were you able to distinguish gravel and rocks from quagga mussels, quagga mussel covered gravel and rocks? I didn't read that very well, but the question is distinguishing gravel and rocks from those that are covered with quagga mussels.
So we were able to distinguish quagga mussels from cobbles effectively. Pebbles and quagga mussels I think are going to be a challenge. We weren't able to do it. If you look at pebbles and quagga mussels, they look very similar. And so in remotely sensed layers, we just couldn't distinguish between those two. If your question relates to gravel, like cobbles and boulders, where some are covered in mussels and some aren't, we weren't able to distinguish between those two, although we did see many examples of boulders and cobbles that were conspicuously absent of mussels. It was one of the questions my colleague Ayman Mabruk had, why certain rocks weren't colonized by mussels.
Okay, thank you. If you hear a dog barking soon, I apologize. I see a delivery person approaching my door. So I'll try to read this quickly. When will the Apostle Island data be available? That's also from Steve.
Oh, that might be another question for Brandon Crumweedy. We just collected the remotely sensed data this year. And I believe the final products are being, the final remotely sensed surfaces are now being shared amongst the project partners to be assessed. There are additional phases to that project, including a plan to go ground truth those sites and begin to develop classified lakebed maps. Those phases of the project haven't started yet, and so will probably, I think, be another year before they start rolling out.
Okay, great, thank you. All right, next question from Julia Hatcher, joining us from Canada. She says, thank you for the presentation. Can you comment on why the LiDAR data was ineffective for benthic mapping in the example you provided? Was it the quality of the data from the specific mission?
So the LiDAR data that we used was collected by others. The U.S. Army Corps of Engineers in 2012. They focused their attention on collecting bathymetry data, and we found that bathymetry alone can to get finer scale information, to find mussel beds and look at colonization of mussels. You really need reflectance data as well, and that just wasn't available in the nearshore Wisconsin LiDAR data set that we used. I understand that the U.S. Army Corps of Engineers repeats those surveys, and in some locations have that reflectance data, which could provide additional information we just didn't have in our project. Thank you.
Okay. Thank you. All right, Margaret Lansing from Gloral asks, are there any near-term plans for more mapping, provided it's safe with COVID?
So, our most near-term plan is our work in the Apostle Islands, where we're thinking about how to get out in the field to collect ground truthing data. So that requires getting on a boat and dropping cameras in the water. We really haven't figured out what COVID does to those plans, other than developing a couple of contingency plans. I know like the talk of bringing the NOAA vessel up here. There's discussion about how to quarantine the scientists that are on the boat. Some of my colleagues at NCOS were able to go on a mapping mission this year after the pandemic started, but there were very stringent regulations and a lot of time required to prepare and quarantine before and after the missions. So COVID is definitely causing a lot of problems with fieldwork.
I'm sure many of us doing fieldwork can relate to some of those challenges. Thank you. Steve Francoeur from Eastern Michigan University asks, using backscatter and intensity data, are you able to differentiate hard surfaces like air rocks or mussel shells from those same hard surfaces covered with softer material such as thick algal mats?
No, I don't think that we were able to do that. There potentially is a way around it, where if you're collecting that sort of information in ground truthing data, you could use a predictive model if those differences are associated with the the shapes, textures, and patterns that you're collecting in remote sensing data. So you could make inferences with a predictive model. I just haven't tested that, so I'm not confident it's doable.
Okay, thanks. We have just 2 more questions in the box, so we'll address those and then wrap up. So Saeed Mamari, again from Michigan State, says, thank you so much. Another question that I have is ground truthing a site-specific property, meaning that for every new field, ground should be done, or can a model be developed that works for Great Lakes once you've tuned in to just one site?
So that question has been rattling around in my head. I'm sure it's been rattling around in others. So when we developed our neural network for Mischli Reef, I was thinking, we have all this data, we have similar habitats nearby. Can we just use the same ground truthing information to extrapolate to those other areas? I haven't tested it, but I think it's a cool thing to try, and I hope someone does at some point. I can see that if you're in a similar habitat, it could be quite effective.
Okay, thank you. And last question from Bopi Badanda at Grand Valley is curious what a white ship is.
So NOAA has a handful of large research vessels that they use for lakebed mapping. And typically they are sent to collect data for nautical charting and for emergency response. They work a lot in the Pacific and on the West Coast, Gulf of Mexico, Caribbean, and along the East Coast. They, in the past, have collected data in the Great Lakes, but I don't think they've been here recently. And so it's a NOAA vessel that has lakebed mapping capabilities and is able to map 24 hours a day for many days at a time, and so you can get very good coverage if they come in.
Great, thank you so much, and thank you for everyone that attended today's seminar. We look forward to seeing you at our next seminar to be scheduled, and thank you, Charles, for the great presentation and taking the time to talk with us today.
Thank you for having me.
Yep. Have a great afternoon, everyone.